All right, so we're back online. But now look at this. So our YouTube officer is not available. Oh, so he's sleeping. Okay, but at least what how I see my phone seems to be it's all right. Okay, so now next we're gonna take a short summary about the mathematics that is needed in this class, and uh, you know, I don't think that the mathematics is a big problem in a class. And why not? Because, there is so much stuff out there. And when I'm saying out there, meaning in YouTube and other sources where you can learn the mathematics. So if you feel shy with certain mathematical details, it's easy to catch up. It's very easy to do so. So let's look at the mathematics. This is mainly for those of you that haven't looked at the mathematics for a long time, or you haven't looked at mathematics in English, because that too could be a little bit of problem. So I'm using the most used terms, so just that you can know what is a, say, diagonal mass or diagonal matrix, what is this and that. So let's get started. So mathematics needed in the course. First, super important observation is this. There's links for Khan's Academy available in a Moodle site. Khan's Academy is one of the famous sites that helps you to learn the mathematics. You know, if you look at the lecture notes consist of several different subjects. Each one of the subjects, there is a link to Moodle Khan's Academy. And you just click the Khan's Academy and you learn like how is a, say, hypothetically, how is a matrix multiplication. If you don't remember that, fine. Just check it out that from the Khan's Academy, or if there is a need to compute, I don't know, if you need to multiply two vectors together and you don't remember how you can make it happen, Khan's Academy will help you to do that. So please use it, and you don't need to search it from the internet, but just log into Moodle site and take a look at the subject listed in a Moodle site, and it helps you to catch up. That's the first very important observation. And again, as I mentioned earlier, this course is not the mathematical course. So the mathematics is a tool set we will use, but we are not going to focus heavily on the mathematics, but rather what is that we can learn and what is what we can do with mathematics. Okay, clear. So now let's look. So we're gonna deal with the matrices quite extensively. And so here's an example about the matrix, and the matrix is called A matrix. And something that we often deal with is that we are looking at different dimensions of matrices. So this is a matrix that consists of m number of rows, and the rows are the ones that are here in this line here, and n number of columns, and the columns are the ones that are located like this. Often we are dealing with the skew matrices, meaning that the number of rows and columns are equal. So there's equal number of rows and columns. That's typically the matrix we are dealing with. And one of the examples that is a skew matrix is a rotation matrix that will be explained to you today. Okay, so that's a matrix. And the matrix consists of n multiplied by n number of components, and they are located in a different rows and columns correspondingly. Okay, so skew matrix, like I mentioned, that's what we are often dealing with. And then sometimes we are using the matrix transpose operation, very basic stuff. What that means is that the diagonal components remains on the original location in the matrix, and off diagonal components would switch their identity. I mean, the rows and columns ID will change their place, meaning that this one here will go here, and this one here will go here. So that's transpose operation. Now, diagonal matrix is another thing that we are often using. Diagonal matrix means that off-diagonal component, which are, in case of 2 by 2 matrix, located here and here, they are equal to 0. Often, we are dealing with identity matrices. Identity matrix is a special case of diagonal matrix. Identity matrix is the one that the diagonal components are equal to 1. 2 by 2 identity matrix. just to give you an example, will look like this. So this is 2 by 2 identity matrix. So it's a special matrix, something that often is needed in a class. Matrix sum operation is very straightforward. So you can multiply, excuse me, you can sum the matrix A and B. Once you do that, you just summing the corresponding components, and what you can get as a result is a matrix C, and here is a operation to make it happen. And again, things are explained in a very fast. The idea is not that you really learn this, but you could just refresh your mind about the different terms. What is a identity matrix and so on and so forth. And then if you're feeling shy about this mathematics, go ahead and refresh your mind using Khan's Academy. Okay, matrix multiplication, that is something that we are frequently using in the class. And that's something that, well, it goes in such a way that you kind of getting the one component, say the one component in a matrix C by multiplying the corresponding rows and columns. So this is an operation that you need to take the corresponding row and the corresponding columns and multiply by these two vectors together. And this is how you get the one single component as a result matrix. You keep on repeating this procedure and you will get the entire solution when you do the matrix multiplication. Example is here. So here's a 2 by 2 matrix, two by 2 matrices. So the first one is A and second one is B, and I'm multiplying them together. So let's look at an example. So first component, I can take this first row corresponding column. So the first row, first column. So I have here 2 multiplied by 3, 1 multiplied by 1. It gives me 7. Similar way, I can move on and I can take the first row, second column, gives me these numbers, and that number that what as I do the math is 11. So this is a kind of what I'm expecting you to know at most, plus some partial operation, but let's not worry about that today. So this is kind of the best, basic stuff we are dealing with over and over in this class. Easy, too easy. You're feeling strong? You have can-do attitude? Yes. Okay, good. All right, so then a little bit about skew matrix and the special thing about the skew matrix. It's possible, sometimes it's possible to compute the inverse of the matrix, and it is denoted such the way that the matrix is with the power -1. That's what the inverse is meaning. And that's possible. So it's possible to compute the inverse if the rank of the matrix is same than number of rows and columns, rows or columns. So it's whatever you want. So it means that there is no independent, all these rows and columns have to be independent with respect to each other. And if that's the case, if you're dealing with the skew matrix, then you can compute the matrix inverse. Then orthogonal matrix is a special thing about this inverse matrix. So orthogonal matrix is something that you can just take a transpose operation, and the transpose operation is equal than the matrix inverse. We will revisit this a bit later today because I'm gonna introduce you the first orthogonal matrix, and it will be the transformation matrix that maps representation on one coordinate system to another coordinate system. This is a typical example about orthogonal matrix, meaning that if you look at the columns of orthogonal matrix, those vectors that you can form from the columns, they are perpendicular with respect to each other. Two-dimensional space is important, easy to understand what the perpendicular condition means. So they have 90 degrees of freedom with respect to each other. Three-dimensional space, perpendicular condition, that too is important, easy to understand. But n-dimensional case becomes very difficult. But you don't need to worry about that because at most we're dealing with that three-dimensional space. So orthogonal matrix, something that you're gonna see a bit later today, and it means that the matrix transpose is equal than the matrix inverse. Basically for us, it meaning like what's the direction of traveling? Are we traveling forward or backward? That's how it can be changed. But we get back to that bit later today. And then the final thing is a matrix, excuse me, the vector operation. So here I have an example vector A that consists of n number of components. A length for this vector can be computed such the way that you take each one of the component, you put it in power 2 and you put them under the square root. Simple like that. Then if we wanted to multiply two vectors together, that's exactly the same operation that in the case of matrix multiplication, this time just the two vectors that are multiplied together. All right, so you mastering the mathematics. You good? Still feeling strong? Still having can-do attitude? And still communicating with me? Good, very good. I know that it's becoming the long day and all this stuff, but now you need to have a deep breath because now things will get started. So we will get started. We're gonna start looking at mathematics, and we're gonna get started from the kinematics. Computational dynamics, roughly speaking, we have two different categories. So we have kinematics, which tells us how the things can be described. And once we set the rules how things can be described, then we're gonna just follow the physics laws to get the equation of motion. Today, we will get started from the kinematics. So we will set the rules how different component will be described. And this is where we're going to start it today. Make sense? All right. So we're going to use, to make this happen, we're going to use a method that is called multibody dynamics. Multibody system dynamics. And first, it's important to understand what kind of system is a multibody system. Well, multibody system, by the definition, is a system that consists of multiple bodies, as the title implies. So no surprises there. But there is one important kind of limitation or definition that is related to multibody system. And that's the fact that in a multibody system, the bodies are connected together via constraints, mathematical constraints, something that limits the motion possibilities. Mathematical description of constraints is physically equal than the joints that combines different bodies together. So that's a multibody system. In a multibody system, we don't make any assumption regarding the magnitude of rotation. So the rotation can be as large as whatever is needed in each one a single case. And this is a big difference comparing what you've been dealing in past. Because if you revisit in your notes from the course of, say, Dynamics 1 or Dynamics 2, you typically deal with the small rotation. Say a pendulum which can rotate like plus minus, I don't know, 10 degrees, 5 degrees. And if you have a case like this, you can have a linear expression of equation of motion for a system like that. Multibody system dynamics, we don't make this kind of assumption. So we can analyze the system that rotates like this much. Scary. So almost hit that mic. So it can rotate like, say, here to here. This is large rotation. And this is a very common source of nonlinearity. So if you're dealing with the large rotation, you're dealing with the nonlinear dynamics. And if you're dealing with the nonlinear dynamics, generally speaking, you have no analytical solution to solve your response. That is not just existing, not possible to do it. So what we're going to do then is that we're going to create the equation of motion that describes this large rotation and connection with the different bodies. And we're going to introduce those equations of motion to computer and asking computer to solve it for us. Makes sense? Remember, large rotation, that is a big difference what you've been dealing in the past and what you're going to deal in this class. Now, I have here two example systems. So I have here a crankshaft mechanism, and then I have here a mass, several masses that are connected together with the springs. One is a multi-body system, another one is not. So which is a multi-body system? Any wild guesses? So hold on. So the first one is or is not? Is. Okay, so you say that this is a multi-body system because, but why not this? This is multiple bodies, one, two, three bodies. It's a linear, but that's all right. I can make this non-linear, so that's not the limitation factor here. Oh, here's my man. Oh, was that a YouTube officer? Yes. Okay, it's because of the constraints, because of the joints. Because the joints couples limits the motion possibilities. And actually, if you look at the crankshaft, it can only move one way. There's only one way it can move. And this way, you can find it out when you take a hold of the piston and you move the piston back and forth. Other bodies will follow with a certain way. How is a way? That is defined with these revolute joints, because we cannot break the joints. And they are mathematical representation, so they will not be break. All right? So with moving one body, I can solve the other bodies by using just the kinematics. So that is a multi-body system. Makes sense? What about this? Here I can introduce the force that is pressing the first body. Maybe the other bodies will follow, maybe not. But I cannot solve position of, say, this body by using kinematics, because it will be moved based on the forces that I introduced through to the springs. Okay? Makes sense? So now you know what's the multi-body system and what's not. Because now is a good time to ask a question, because what follows is a class quiz. I'm going to ask if you're not going to ask for me. Clear? This is not the multi-body system because the bodies are not connected together via constraints. They are connected via spring element, force elements. So that's a different story. So it's not the multi-body system. Any other questions? Okay, so let's go. What's not the multi-body system? So let me put the class quiz on. So next. Okay, so let me explain what I have here. So what is not the multi-body system? So I have here a building, then I have here an excavator, I have here 4-bar mechanism, and Elvis. One out of the 4 is not the multi-body system. But which one is not the multi-body system? That I would like you to enter your answer to Socrative system. Okay, while you want to have some time to think about it, and it's all right to consult your fellow student too. I mean, if you trust that your fellow student is good enough that knows the answer to this question. If, then it's all right to do it. And then you can come here too, and I will tell you which is the correct answer. Just come here and I will whisper it to you. That's one option too. So, but you need to come here. I'm not going there. Okay? You want to have some time to think about it, or you just know what it is? Okay, so let me take a look. So let me check how, and this again is not visible for online participants. I see that I have 79 students, and roughly half of them already entered the answer. Go ahead and discuss with your friend. It's all right. But don't be mad to your friend if he or she is saying the incorrect answer. Okay. So while you're thinking, let me move on. So what we're gonna do next is that we're gonna start looking the description of body. Remember, the whole idea, what we're aiming to do today is description of rigid body. So let me go back here. Description of rigid body. So we're gonna first describe the one rigid body, and that we're gonna do over and over and over again until you are very bored about that. But that is just the kinematics we keep on repeating. Okay? So let's get started from the body. You know, something that is very important to you to understand that, we have a body, and the body can have any shape, like beam-like body, this one, or potato-shaped body, the one that is shown in my slide. But when you look at the deep, like what are the ingredients that makes a body? In our, in mathematical perspective, the body consists of particles, infinite number of particles. So there's a lot of particles. By the way, particle is a mathematical definition. So it's not something that kind of it exists in reality, but how we are looking at the particle is like more like mathematical definition. So you cannot go the nearest grocery shop and say, I want to have a bunch of particles. That's not possible, because particle is a mathematical definition. And we are looking at the particle like the one that makes the body to exist. All right. So what's so special about the particle? Special thing about the particle is that it's very small. Again, how small? Don't worry about that. This is just the mathematics. Now let's call it small particle. And when it is small particle, what is important is that it don't have a rotational degrees of freedom. It's just a dot. It's just a dot. If the dot is like this orientation or this orientation, makes no difference, because it's just a particle. It's a tiny, tiny particle, and that's why it doesn't make any difference. Now, something other also very important to understand is that there's a lot of particles within the body, infinite number of particles. So it's not just the three particles like shown in the figure, but a lot, mathematically infinite number of particles. So there's millions and millions and millions of particles, a lot of particles. Each one of them that's just a dot, single dot. Now the special thing about mathematics, why we wanted to deal with these particles, is that while they don't have a rotational degrees of freedom, it is very simple to describe them mathematically. Because, you know, think about the particle, the one that is shown here. It only have, I can describe that with respect to my global coordinate system by using a vector R. A vector R, consists of two components, which is a projection in a x and y direction. That's it. No rotational degrees of freedom, because it's a particle. Clear? All right, very good. So how is a multi-body system? So this is like a schematic representation. So multi-body system is what we are looking at. So multi-body system consists of bodies. And I have here an example. So it consists of three bodies, right? What is something that connects these bodies together is a joints. So joints make them interact with each other. It's actually limiting the motion possibilities within these bodies. All right. So example could be that crankshaft mechanism. So I have revolute joint, and then the piston and the revolute joint. I have here 1, 2, 3 bodies, like shown here, and they are connected together via joints. All right. And then each one of the bodies, they have a lot of particles. So when you look at the inside of the bodies, they consist of infinite number of particles. So a lot of particles. So that's the kind of like a schematic representation of multi-body system dynamics. What we're going to do next is we're going to define one particle, could be this one here, with respect to reference coordinate system. And the reference coordinate system is the one where everything is measured respect. So typically, this is a system that has many different names. Sometimes it's called as a global coordinate system, sometimes with a different name, but that's the reference coordinate system. And typically that reference coordinate system is the one that is not moving, but is standing still. Clear? All right. So again, I have these three particles. In theory, I could describe these three particles by using just a vector that leaves here from the reference coordinate system and ends wherever the particle is located at. I could do this. I could. But you know that this is kind of like a dead end for us, because now when I describe the three particles using this technique, I already have quite a few number of variables, because this one here is a vector that consists of how many variables? Two, because x and y projections. And then I have here another vector that consists of how many variables? 2. So I have already 4 variables. And then I have here one more, so it's 6 variables. And still there is huge amount of particles not described yet. So this is not working out. So I cannot use this kind of technique. So I need to figure out something more clever than that. What that could be. Well, as mentioned here already, you know, what is important to understand that these particles, they cannot move with respect to each other. Why not? Because they are within the rigid body. And by the way, the rigid body is something that is again mathematical definition. There's no such thing like rigid bodies. Every particle will deform if huge amount of force is imposed to it. But mathematically, we can make an assumption that there is a rigid body. All right. Now, if there is a rigid body, these particles, they cannot move with respect to each other. Like say vector u bar that is shown here will be constant all the time. So it cannot change as a function of time. It cannot. All right? Makes sense. Using that observation, we can introduce alternative or additional coordinate system. And this additional coordinate system is called body frame of reference coordinate system. So now I have 2 coordinate systems. I have my original reference coordinate system, which is, let's call it that as a global coordinate system. And then I have my additional coordinate system, which is a body reference coordinate system. Body reference coordinate system is attached to body. It's welded to body. So body translate, the body reference coordinate system will do the same. If body rotates, the body reference coordinate system will do the same. Why we do this? Well, the reason is this. Now, with help of this body reference coordinate system, I can describe particles with respect to body reference coordinate system, and that description remains constant. So it's beautiful then. So then I can describe not just the 3 particles, but all these infinite number of particles, because the vector u bar that can scan every single corner of the body, and with the integration procedure, I can now count all the particles that is within the body. So it makes sense. You with me still? This is like, is it a little bit boring? It's too easy. It's all right. It's all right. Okay. So you can also do this, like speed up, speed up. I want to, too slow. It's all right to do that as well. Any comments from online participants? Are they saying that please speed up? Okay, not yet. Slow down. So it's like do nothing. Okay. All right. So, but you with me, so you understand the concept so far. Okay. Now, this is a concept. So I can describe particle. Again, remember my overall objective, the mission, the reason that I'm doing this is that I want to describe all the particles with respect to my global coordinate system, this coordinate system. And now I'm doing that with the 2 steps. So I'm first introducing the vector that is starting from the origin of the global coordinate system, and it ends the origin of the body reference coordinate system. So that's halfway done. I'm not yet there, but I'm very close to it. I'm almost there. So the one more step that I need to do is that I need to travel here from the body reference coordinate system to point where the particle is located at. That's it. So then I can describe the particle with respect to my reference coordinate system, which is the global coordinate system. 2 steps. Okay, makes sense. Now the only problem I'm facing here is that when you know body is rotating or translating, projection of vector u bar, this one here, with respect to global coordinate system is moving all the time. It is changing all the time. You see that? Because if I first describe the u bar here, and moving here, projection is moving all the time. So I need to figure out the way to map my representation from this coordinate system, which is a body reference coordinate system, to this coordinate system, which is a global coordinate system. So I need to find the relation between these two coordinates. And once I have that, mission accomplished. You know the reason? You're still with me? You know all the steps why we do this. Okay, so by the way, now you need to do it like this, or what the heck is this thing? Like none of this stuff makes any sense. I don't know. So you're good. Okay, so let's look something entertaining in the meanwhile. So let's look how is that we're scoring in-class quizzes. Okay, so not all the students entered the answer, but some are still coming. 10 is still missing. Okay, what is your expectation about the success rate? Guesses. So this is lottery. So guesses. So okay. So you did a mistake. So it's not going to be 100%. That, by the way, never ever happens 100%. Once it was close, but then it failed. If it happens, I'm going to take a picture of that. I'm going to send that to rector. Like, look at me. So I'm an outstanding teacher. So every single student knows this correctly. But what's the percentage? My guess is 72. 80. Others 65. Okay, you don't want to play with me. So, okay, so let's see. Oh, 77. So I don't remember what you said. You said 50. Yeah. Elvis is about multi-body system. Mechanism is a multi-body system. The building is not because it's not moving. It's one chunk. It's not moving. So it's not something that connects with the body. So you argue against me. Yeah, that's a good one. I like this. So you want to get the points if you say building. I mean, if you say something else than a building. So what is then not the multi-body system? What is it you say? Elvis, come on, Elvis is what we are following. Elvis is the most important person in this class. But you say Elvis because of the biomechanical system. I like your argument. So I like this so much, but let's put it Elvis as also the correct answer. Happy? So what that then makes us, oh my God, 99%. 99%, but not 100. All right, back to the business. So this is again is something that online participants, they don't see it. So what we're gonna do then, this is important observation because of the body translation and particularly its rotation, you cannot just sum these two vectors together. Why not? Because they are represented in different coordinate system. One in global coordinate system, this one, another one in a body reference coordinate system. So it's kind of like apples and bananas, or I don't know, however they explain it is in I don't know, junior high school, or whatever they're using these bananas and apples. So they don't match. They're in a different coordinate system, so you cannot sum them together. So you have to first convert them to be in the same coordinate system, and then you can add it. All right? So how I can make it happen? Well, I can make it happen by simply looking at the projections of this vector u bar in a global x and y direction. It is simple like that. So how it goes? I have here my vector u bar, and the vector u bar, two important notations here is this. First of all, the body reference coordinate system is rotated, that is amount of angle that is equal than the theta. So it's rotating amount of theta. All right. Then I have another important angle, and that angle is how is angle of vector u bar with respect to orientation of body reference x-axis. That is denoted as alpha. So I have two rotations. You put them together, you will get this angle, how much the vector u bar is rotated with respect to global coordinate system, right? Okay, so then it is easy if we know this. So then the first one here, so we look at the projection in x direction, which is this one here. So it's very simple. As I'm gonna just take the vector u bar, its length, right? Because I'm looking at the scalar number, so it's a vector length. And then I'm gonna take the cosine from the angle that is alpha plus theta, right? Because I'm looking, oh, this is becoming messy, but I'm looking this one here. And obviously you can get it by using cosine, right? By the way, I was just, yesterday, my son was learning these trigonometric functions. I was refreshing my mind about the trigonometric functions. I'm really strong about these trigonometric functions. So don't challenge me in that. All right, so let's move on. So then y direction, this direction, how that goes. We just repeating so we're gonna take the length of vector u bar, and this time we're gonna take the sine from the angle that is alpha plus theta. Okay, that's it. We're almost there, almost. We just need one trigonometric relation that we can utilize, and the relation is this one here. So the cosine alpha plus theta can be expressed as it is shown here. Where that is coming, no idea. It's just the mathematics. But that's all right. There's a bunch of these rule books available out there. So you just take the one and copy it directly there. Simple like that. No thinking. By the way, in multi-body system dynamics, generally speaking, no thinking is allowed. No thinking. You just follow the certain procedure and you will get out everything automatically. Don't think. All right. So then, so I'm going to use this one here, and then I'm going to use this one here. I'm going to substitute this relation to these equations, and this is how the projection looks like. All right, just the mathematics, nothing else. All right, then I'm going to use a notation which is extremely important to me, because I want to take a look, I want to see what is a vector u bar projection here in with respect to body reference coordinate system, and that can be expressed in such a way that is again the length of vector u bar, and then cosine alpha. Look, this time just an alpha, not alpha plus theta, but just an alpha. And then here the same thing with respect to y projection. So it's a length of vector u bar, and then the cosine alpha. Once substituting that information to previous equation, I can express the relation between the vector u bar and vector u, which is its projection to global coordinate system. Look what I have. Here is a representation of vector u bar in a global coordinate system, and here is original vector u bar. Mapping. The maps is introduced by this 2x2 matrix, which is called rotation matrix. It is the magic thing for us. It is the one that is moving the representation from one coordinate system to another coordinate system. This, by the way, is an orthogonal matrix. It's a 2x2 orthogonal matrix, meaning that if you form vectors out of these columns will be perpendicular with respect to each other. Meaning that if you want to take an inverse of this matrix, you can simply do it by using transpose operation, like we discussed earlier today. Okay, so now I have this magic relation that moves the representation from the body reference coordinate system to global coordinate system. And that's possible with help of this 2x2 rotation matrix. And that's it. Now this is it. Almost there. Just remember, there was still this first step when we move from the origin of the global coordinate system to body reference coordinate system. Let's just account that, and we have end of the story. Excited? Okay, relatively excited. Okay, so here is end of the story. So this is how it goes. So I have here the vector r, which is where the particle is located at with respect to global coordinate system. And this will be expressed by using two steps. First, we're traveling from the origin of the global coordinate system to origin of the body reference coordinate system. Okay? Then we're going to map two coordinate systems that are body reference coordinate system and the global coordinate system, and that will be carried out with help of this 2x2 rotation matrix. And once we do that, it converts this vector u-bar representation to be in a global coordinate system. Guess how many times I'm going to repeat this equation during this time, during this course? 5 million times, correct. You said, was it 5 million or what? Yeah, 5 million times. So it's going to be over and over and over again. Why? Because this is kinematics. So we just set the rules how everything will be described. So this is it. This is almost the nuts of the course. Just a few details in a way, and that's it. But now we have the way to describe the particles. Next, we're going to account all the particles, all the bodies, constraints, so on and so forth. That's it. But over and over again by repeating this equation. Okay, it's like this. Okay, good. Questions? Can I ask in class quiz regarding this subject matter? Can I? Ah, it's very strong. It's like, I will not. Just testing. Okay. Uh, what is this? Okay, here's an example. So we're going to look 2 examples and then we're going to go back home. So that's it. So again, no thinking, just repeat, substitute. Substitute, follow the steps like no thinking, and that is the success of this in this class. All right. So I have here a beam-like body, and a beam-like body is made such the way that the body reference coordinate system is located at the end of the beam-like body. And by the way, in a multi-body system dynamics, the body reference coordinate system can be located anywhere you want. Anywhere you want. Within the body, outside of the body, center of the mass, whatever you want. There is one thing that is good you to know already this time, that sometimes it helps to simplify the equation of motion if you put your body reference coordinate system in the center of the mass. But that only helps in two-dimensional cases, in planar cases. In spatial cases, three-dimensional cases, the improvement is marginal. So you can put it anywhere you want. Now here is a case where the body reference coordinate system is located in the one end of the beam-like body, and the body reference coordinate system is rotated amount of theta, and theta is p divided by 2. That's 90 degrees. All right? And I'm asking where the particle p is located at with respect to global coordinate system, and the particle p is another end of the beam-like body. Can I solve it? Yes, I can solve it because I have all the information that is needed to carry this out. First, I just travel here to origin of the body reference coordinate system. How can I make it happen? Here is the numbers are given to you. So I'm just going to use the vector where I'm first traveling 2 units in a x direction, 1 unit in a y direction. That is a number that is provided in a question. Okay? Here is a translation. Then the rotation. How can I do that? Simply taking this theta information, which is given here, and substitute that in the 2x2 rotation matrix. That's it. And now comes the difficult part. How can I define the vector g bar? Only way to make it happen is that you have to put yourself to this place, origin of the body reference coordinate system. You need to be here. Sorry that this is a bit messy, but I guess that I cannot clear this at the moment. So you here, you need to travel here. So how you can make it happen? So you have to start walking along the body reference x coordinate axis. Correct. How far you need to walk? Until the end of the beam? How is that you know the length of the beam? Well, it's mentioned here, so it's 1. So you walk here along the x-axis, because the x-axis is the one that is pointing upwards. Yes? No? No, it's x-axis. Yes, because it's rotated 90 degrees. Okay, so I have here, by the way, if you look at my YouTube channel, there is this thing testing coordinate system. This is our gang sign. I'm going to explain where that is coming next week. But next time you see me in a corridor, you don't say hello, Aki, but you say respect. It's a spatial coordinate system. We're using that all the time. Well, not all the time, but a little bit of that. So that where, but again, so it's x-axis originally is like this is x-axis, and it's rotated 90 degrees. So it's like this. So I'm traveling along the bend, this direction. How much? 1 unit. How much I need to travel to this direction? 0. So this is the U-bar component. Rest is a math. And once the question like this is asking, like I'm asking you to do the homework, use a symbolic math tool, because why not? So what are the symbolic math tools? There's a many different options. MathCAD is one. Mabel is one. MathCAD, I think that you can upload it for free for 90 days, I don't know, 30 days or 90 days, something like that. I recommend to use that. MATLAB, they have a symbolic tool set, so that's one option. But use the symbolic mathematics, because you can easily introduce a mistake when you do it by using a pen and paper. And also is a lot of work. Okay, that's it. Final example is this. So I have just shortly, let's take a look at this. So I have here, again, the beam-like body. Now the x-axis is pointing this direction, and I need to travel this end of the beam-like body. Now the body reference coordinate system is located in the middle of the beam-like body. Okay, and now it's mentioned that the length of the body is 2 units. So this in total is 2. All right, so first I travel here. That is provided here. So it's a 1, 1. Then I'm counting my rotation, which is provided here. So it's 3 multiplied by p divided by 4. And then the only remaining difficulty is a vector u bar. How can I travel the vector u bar? I'm at the moment here, and I'm looking this direction, x direction. But how can I be here by traveling the minus direction, x minus direction? You got it? Because I'm looking this direction, and this is where I need to go. So I'm traveling minus 1. How far I need to travel to this direction? 0. So minus 1, 0, you do the math, that's how it looked like. Now, this is it. So it's already 6 o'clock. Time to close for today. If no questions or comments.
Will you be adding these slides to Moodle?
Yes, everything will be Moodle. Everything, like I said, that if it's not in the Moodle, you don't need to learn it. Simple like that. But no, that's not completely true, because recordings will be not in the Moodle, but in the YouTube. Yes, sir.
So during exam, for example, are we also allowed to use this MathCAD, or
Yes. That's why it makes sense to use this to make these symbolic tools ready for your exam. So you can use whatever you want, except you cannot use your mom and dad. You cannot use your friends. Oh, by the way, I forget there was a question about the enrollment. How to enroll to, you were the one that were asking, how is it you can sign into midterm exam? You don't. It's just that I'm going to open the website for you, and then you log in with your personal ID numbers. That's it.
for a week?
For a week. For a week. And you can use every material you want. You can use Google. You can even call me, but not your mom and dad. That's again not allowed. So use whatever you want.
So also the week 51 exam is for a week,
Same stuff, 1 week.
and
You can do it whatever you want, wherever you want, except that you have to have a strong internet connection. So once you click it on, you cannot reverse. You cannot say, oh my God, I have no knowledge in my head. I want to undo this. You cannot. Okay, you good? Are you coming back next week? You shouldn't. You shouldn't, because you should follow this using the streaming. Yeah, of course you can come back. Please come back. It's more fun this way.